Welcome to our second topic in quantitative analysis for business decisions. And today we are going to look at linear programming. We are going to see, sorry, we are going to see how we can use the knowledge of linear programming in we are going to see how we use linear programming when it comes to making business decisions. Okay. So we want to understand what linear programming is all about. And you will realize that linear programming, or what we call linear optimization, may be defined as the problem of maximizing or minimizing a linear function that is subjected to linear constraints. The constraints may be equalities or inequalities. So what are we trying to say? Here, for example, if you are to optimize profit and even revenue, and you are doing it not in a free condition, but in a restricted condition, meaning holding other factors constant for you to be able to achieve this. And therefore, that's what brings about the constraint. On the same basis, the aspect of minimization comes along when we are talking about cost of production. So how can we minimize cost of production? And therefore, how can we minimize losses in business endeavors? So the optimization problems involve the calculation of profit and loss. So linear programming problems are an important class of optimization problem that actually helps to find the feasible region and optimize the solution in order to have the highest or lowest value of the function. So with the constraints, we are going to come up with a feasible region. In business, we operate in feasible region, within which the boundaries within which to operate, to make decisions as a business manager are clearly outlined, and this could be within the policy of the business or in other documents, guiding documents and manuals that form the constraints. So in other words, linear programming is considered as an optimization method that is maximize or minimize the objective function of the given mathematical model with the set of some requirements which are represented in the linear relationship. What this statement tells us is when we are talking about optimization, we optimize maximization, we optimize minimization. So what it means is this. So if you are talking about profit, how do we maximize profit? When you maximize profit, you will have optimized whatever you are looking for. Whenever you minimize losses, you have optimized what you are going for. That is how I want you to understand. The main aim of the linear programming problem is to find the optimal solution. To find the optimal solution. To find the optimal solution. So what we are trying to say is that we are looking at the aspect of, okay, Just a minute. Okay. So some of the assumptions taken while working with the linear programming are: number one, the number of constraints should be expressed in the quantitative terms. Number two, the relationship between the constraints and the objective function should be linear. Number three, the linear function, what we call objective function, is to be optimized, meaning if the objective function is revenue or profit function, then this must be optimized by maximizing revenue, maximizing profit. And in any case, it is a loss function or production function, then we optimize when we are minimizing the cost of production as well as the loss. So there are components of linear programming. That is, the basic components of the linear programming are as follows. Number one, decision variables. So we need to have decision variables where in a function we would be having the independent variable and the dependent variable. Therefore, whatever manipulation you carry out in the independent variable is or are likely to bring about changes in the dependent variable. And constraints, this would give us the feasible region or the area within which we operate, which is governed, which is sort of given boundaries, so that we don't make decisions beyond the boundaries, but we are within a given feasible region within which we have to be able to achieve optimization of whatever objective function we have. Then we need data, meaning we need information that will help us in actually determining whatever decision we are likely to make in as far as the linear or whatever we are calling objective function is concerned. So yeah, so we need objective function. This is the main function that has to be optimized. And so we want to look at characteristics of linear programming. Linear programming must have constraints. Yeah, must have constraints. In this, we are trying to say that we are trying to simply say that the limitations should be expressed in the mathematical form regarding the resources, So, in other words, what we are trying to say is that there should be also linearity, meaning we are dealing with the linear arrangement. Therefore, there should also be fitness, meaning there should be finite and finite input and output numbers. In case if the function has infinite factors, the optimal solution is not feasible. Then non-negativity. So we are dealing with variable values which should be positive or zero. So it should not be a negative value. Then when we talk about decision variables, we are simply talking about the decision variable which decides the output. It gives the ultimate solution of the problem. For any problem, the first step is to identify decision variables. So decision variables are very, very important. They are very important. So let us go to linear programming problems. So we are saying the linear programming problems is a problem that is concerned with finding the optimal value of the given linear function. The optimal value can be either maximum value or minimum value. So here, the given linear function is considered an objective function. So the linear function is considered objective function. So the objective function can contain several variables, as I've said before. For example, we would be having the dependent variables, we would be having dependent variables, we would be also having intervening variables. Intervening variables are variables that are beyond our manipulation. So the linear programming problems can be used to get the optimal solution for the following scenarios, such as manufacturing problems, diet problems, transportation problems, allocation problems, and so on. What of methods to solve linear programming problems? I'm saying that the linear programming problem can be solved using different methods, such as the graphical method, simplex method, or by using tools such as R, OpenSolver, etc. So here we will discuss, that is in this topic, we are going to discuss the most important technique called the graphical method in detail. So the graphical method has variables, and this is to give us the variable linear programming. If the problem has two decisions variables, the graphical method is the best method to find the optimal solution. So you can see, like when we are making decisions in our businesses, we don't rely on just one variable. We do try to get several variables. For example, in the industry and the market, for us to determine what we want to do. So in this method, that is the graphical method, the set of inequalities are subjected to constraints. Then the inequalities are plotted in the XY plane. Now, once all the inequalities are plotted in the XY graph, the intersecting region will help to decide the feasible region, meaning the feasible region will provide the optimal solution. But within the optimal, we can maximize, we can minimize. So let us use an example here and understand the concept of linear programming in a better way. Example here, you're being told, calculate the maximal and minimal value of z equals to 5x plus 3y for the following constraints. And the constraints we have here are x plus 2y equal or less than 14. Second constraint, 3x minus y equals or greater than 0. And the third constraint is x minus y equal or less than 2. So the solution will be, once we plot these constraints on XY plane, and you will find that they will give us a feasible region within we can be able to decide what we are looking for, or rather what I'm saying to be optimization. of the objective function. So the optimization equation is z equals to 5x plus 3y. Therefore, you have to find the xy corner points that give the largest and smallest values of z. So within the feasible region, you can be able to come up with a point, xy point, that gives the maximum, and xy point which gives the minimum. So to begin with, first solve each inequality. Yeah. So you can see we simplify the inequalities we've been given. So like the first one was x plus 2y equal or less than 14. Now we want to get the function y. So we make y the subject by either dividing, subtracting y on both sides, and we end up getting y equals or less than minus half x plus 7. When it comes to 3x minus y equal or greater than 0, you find that when you make y the subject, what you do here, first of all, you will subtract 3x from each side. Then you end up by also subtracting y from each side. End up with y equals or less than 3x. When it comes to x minus y equal or less than 2, this will make y the subject, and this will give you y equals or greater than x minus 2. So here is the graph for the above equation. Here is the graph for the above equation. So I want it to be seen properly. Okay, so you can see all that is plotted. Therefore, we move forward. And now, what do? Now pair the lines to form a system of linear equations to find the corner points. So first of all, we take the first two. We pair them. Then we solve the above equations. When we solve them, we get the corner points as 2, 6. Because when you equate this, you will solve for y. And when you know y, you substitute for x. And when you do that, you'll be able to have known 1 point, xy, in as far as those two lines where they are intersecting, and that is the maximum point. Then we take the second, we take the first and the third. You know, we took the first and the second. Now we are taking the first and the third, and we solve the same, and we get the corner points as 6, 4, 6, 4. So we move forward. Now we take the second and the third. Remember, we took the first and the second. We took the first and the third. Now we have taken the second and the third. When we solve, we get these points. And this would be the lowest point in as far as that feasible region is concerned. So for linear systems, the maximum and minimum values of the optimization equation lie on the corners of the feasibility region. Therefore, we find for all this, we can now substitute in this equation, And when we do that, you can see when we use the first 2 points, when we paired inequality 1 and inequality 2, we got these points. So when we substitute them, they give us 30. So we go forward, we go to the second one. We do the same. It gives us, sorry, let me see. Is it really 30? Just a minute. This is 6. It's not really 30 because this is 6 and this is 18. So this is 6, that's 18, and it will give you 24. It will give you 24. Yeah, it will give you 24. Then we go to the second one. Second one is 18 plus 12, and this gives you 30. Now the third one, when you put this is -3 plus -12, and this gives us -15. So you can see that this is the optimization point. Hence, the maximum of Z equals to 30 lies at 6, 4, and the minimum lies at that. So that is it. So you can see we've been able to find the maximum and the minimum. So we have optimized. So if the objective function was revenue or profit, then we would have been able to plot the highest point at which we can maximize revenue and profit. And therefore, so the question is, what would be this constraint? When we are doing production, we are using labor, we are using materials, we are using finance and whatever. So whichever combination, for example, what would be Y, what would be whatever variable that is being used to determine. So let us, now this example is for student self-practice, where I'm saying a company makes 2 products, X and Y, using 2 machines, A and B. Each unit of X that is produced requires 50 minutes processing time on machine A and 30 minutes processing time on machine B. Each unit of Y that is produced requires 24 minutes processing time on machine A and 33 minutes processing time on machine B. So at the start of the current week, there are 30 units of X and 90 units of Y in stock. So the question is, formulate the problem of deciding how much of each product to make in the current week as a linear program. To solve this linear program graphically. So find let X be the number of units of X produced in the current week, Y be the number of units of Y produced in the current week. So when you do that, this is what you come up with, and it takes you do substitution in the objective function where you maximize until finally you'll be able to get this amount. So this becomes the graph. Then when you solve it simultaneously rather than by reading values of the graph, we have that X equals to 45 and Y equals to 6.25. with the value of the objective function being that. When you substitute these two in the objective function, that's what you're going to get. So linear programming applications is done in really life. Like you can see when we are working on the efficiency of manufacturing, energy industry, transportation optimization, especially when we are looking at cost and time efficiency. When it comes to importance of linear programming is broadly applied in the field of optimization for many reasons. Like, for example, many functional problems in operations analysis can be represented as linear programming problems. And many others, especially when we are looking at algorithm for the solution, especially in transportation problems and assignment problems. So there is what we are calling sensitivity analysis. So what do you mean by this? Sensitivity analysis is a financial model that determines how target variables are affected based on changes in other variables known as input variables. So like this model, sensitivity model, is also referred to as what if or simulation analysis. It is a way to predict outcome of a decision given certain range variables, or what we could calling constraints. Yeah, so an example of sensitivity analysis, one simple example of sensitivity analysis used in business is analysis. It's an analysis of the effect of including a certain piece of information the company's advertising. Because you remember, one word in your advert can influence consumers, and one word can even chase them away from you. So that's how you could want to find out how sensitive the word you want to use in advertisement could be in the mind or attitude of customers. Yeah, so this is very important for us, and therefore sensitivity analysis can reduce a false sense of security by giving a range of values for net per value return instead of a single value. So it identifies the variable that has the most effect on the net profit value. The net profit value. So here is students on practice that I would want you to go through this, and when you do this, remember, practice makes perfect. So the many times you do this linear programming calculations, the more you become familiar, and if not very much acquainted with linear programming as far as business decision making is concerned. Otherwise, if there is no question, no comment from you, I would want to call it a day and wish you success as I look forward meeting you in our third lesson, where we shall be looking at inventory models. Otherwise, thank you very much. Enjoy your time.